Suppose that there's a playground. On the playground, there's a merry-go-round. Merry-go-round is as shown here. We're viewing this merry-go-round from a side angle, and the radius is 1.6 meters. So from the center to the outer circumference, R equals 1.6 meters. Now the moment of inertia for this merry-go-round is already measured to be 260 kilograms meters squared. So I'll write it up here. Your I value, your inertia, this is equal to 260 kg times meters squared. Okay? Now, this merry-go-round is rotating around a vertical axle, as shown right here, vertical. Now, there's also a child. The child hops onto the merry-go-round right here. Okay, and the child, even though his head is a little cut off right now, his mass, all right, mass of C for child, this is equal to 24 kgs, kilograms. And the initial angular speed that this merry-go-round is traveling initially, okay, we'll write it down here, your I, angular velocity initial is 11 revs per minute. Hello. Today, we are going to be working on some rotational energy problems. You're welcome to watch, maybe learn a little bit, maybe just have it on while you're studying, or anything you want. It's up to you. But with that, we have our values for this problem currently, and let's get to solving it. So firstly, we're going to take the initial angular velocity and we need to convert it to radians per second. All you have to do here, we're in revs per minute. So if you multiply by 2 pi radians over 1 rev, there's 2 pi radians in 1 revolution. Okay, and then at the same time, we want to multiply by 1 over 60, because there are 60 seconds in 1 minute. This will get us our answer. Let me calculate it real quick. $11 times 2 pi times 1 over 60. This will give us 1.15 radians per second. So I'll put it right here, right on the edge of our paper. Put it right here, right on the edge of our chalkboard. It's a little tight over here. It looks like we are going to be using angular momentum. This is because what we're actually trying to solve for is the final angular velocity after the child sits on the merry-go-round. So we're actually solving for the final angular velocity, denoted by this question mark right here. So what we were able to do is find the initial angular momentum. We can find the new moment of inertia with the child on the merry-go-round, and then we can set up an equation applying conservation of angular momentum to get our final angular velocity. So the initial angular momentum equation is L I, we'll add a subscript, L initial equals moment of inertia times the initial angular velocity. Now, to apply conservation of angular momentum, we can take this equation and equal it to angular momentum final. So it will look something like this. This is angular momentum initially, and then this is angular momentum final. The two will be equal to each other. On this side, we're using the new moment of inertia, which we will find shortly, and the final angular velocity. And we get this equation simply by using different values to find the same thing, but after the child has sat on the merry-go-round. So let's find this new moment of inertia. So after the child sits on the playground, our new moment of inertia is going to be the previous moment of inertia we already know, plus mr squared. This is from the parallel axis theorem, where we are able to take the moment of inertia of just the merry-go-round and add it to mr squared. Plugging in values, we'll get in equal to moment of inertia of just the merry-go-round, which is 260 plus, that's a really bad plus sign, I must admit. I apologize for my plus. That's a little messy. Plus the mass. So our mass right here is 24 kilograms. We're taking the mass of the child being added on. And since the child is sitting down on the edge, we can use the same radius, 1.6 meters. That's the distance he is from the center. So we can use r in our calculations, 24 times 1.6, and then we have to square it. we needed a little bit more space, so I moved the camera down a bit. Our new IN value will be equal to this above. To calculate it, we'll put in 260 plus 24 times 1.6 to the second power. This will answer. This will give us 321.44. This is in the same units as before. Kilograms, meters per second squared. Oh, excuse me, I apologize. Kilograms times meters squared. Now we have this value. Now that we have all of this information, we have enough to solve for the final angular velocity. The moment of inertia initially is 260, and this is multiplied by the initial angular velocity, 1.15 radians per second, and this will equal 321.44 times W final. Whenever I say W, I mean angular velocity. I just like how the symbol looks like a W, so I often just call it W. It helps me remember it a little better. So, to solve for angular velocity, we'll divide this side by 321.44. And we'll do the exact same thing on the other side. And just like that, we have our answer. So let's solve it. The final angular velocity. To calculate it here, we'll have 260 multiplied by 1.15, which is 299. Then we'll have this divided by 321.44. And this will give us our final answer in radians per second. And there you go. And we're going to leave our answer in radians per second, as that is the more accepted unit in rotation. Okay, so for this next problem, we have an inclined plane, as shown here. Add a little bit more to it, and it's on a level surface. We have a solid sphere at the top of the inclined plane. It's going down inclined plane, and it starts at a height of 8 meters. This is equal to h. Now, this sphere has a mass of 3 kilograms. Now, what we're going to be solving for is the velocity final at the end of this inclined plane. So right at the end there. Now initially, when I tried doing this problem, I solved for the final angular velocity, but that doesn't work because you would need to know the radius of the sphere, which they don't give us. So instead, we're going to find velocity final. So, what we know is that this object at the top of the ramp has a potential energy of mgh. And it's also important to note that this system here has no slipping. This will be helpful to know later, and I'll tell you why. So, we have mgh, and this will be equal to the final kinetic energy plus the final rotational energy. This works because there's no slipping in this system, so everything will be conserved. So it'll be 1/2 mv squared, your final kinetic energy, plus 1/2 I angular velocity squared. Now the issue is we don't actually know what our angular velocity is, so we cannot solve for v squared. So we have to do a little bit of algebra here. So what we can do is we can plug in the moment of inertia for the solid sphere, which is 2/5 mr squared. And this is multiplied by angular velocity squared. Now this is important because when there's no slipping, which I'll put it up here, v is equal to angular velocity times r. When there's no slipping, velocity is equal to angular velocity times the radius. And right here is the radius squared multiplied by angular velocity squared, which means that this simplifies to v squared right there. So that means we can rewrite this equation as mgh equals 1/2 mv squared plus 1/2 times 2/5 is 1/5. Well, it's 2/10 simplified to 1/5. So plus 1/5 m, and then r squared times angular velocity squared simplifies to v squared. Now we have two v's squared in both of our terms, so we can take out the v squared like so, and then we can divide all of this by itself on both sides to get v squared alone. So that would simplify to v squared equals mgh over 1/2 m plus 1/5 m. Like so. All there's left to do here is square root both sides, like so. And then we can plug in values. V equals square root of 3 times g, which is 9.8 the force of gravity, or the acceleration of gravity, I apologize, multiplied by the height, which is 8, the height that started at. And then we can do 1/2 times its mass, which is 3, plus 1/5 times its mass, which is also 3. And this whole thing will give us our final answer. Now, by plugging this in, we should get square root of 3 times 9.8 times 8 on the numerator. Then on the denominator, 1/2 times 3 plus 1/5 times 3. And our final velocity at the bottom of the inclined plane is 10.583 meters per second. And there you have it.